Welcome to the final section of the course. You have come a long way from creating a simple LED class to mastering inheritance and non-blotting Init. Now, it is time to put all those pieces together to build our capstone project, a traffic light system. This project is designed to challenge your OOP skills and show you how to structure complex real-world logic. This is the edited final circuit. We aren't just making LEDs flash. We are building a modular system. We will create a traffic light class that manages 3 LEDs and transitions between states: red, green, and yellow. We will also integrate Potentiometer to control the brightness of the LEDs in real time using pulse width modulation, all while keeping our code clean and object-oriented. The biggest challenge here is the state machine. Instead of using a giant switch case in your main loop, the traffic light object itself will decide when to switch from green to yellow based on its own internal timer. This is the ultimate example of encapsulation. Our architecture will look like this. The main loop will simply tell the traffic light to update and the potentiometer to read its value. The traffic light class will act as a manager for our LED objects, and the potentiometer class will provide the data needed to adjust the brightness levels. It is clean, scalable, and professional. Are you ready to build something impressive? Let's get started. In the next lecture, 07.02, we will define the interface and set up the main program structure to kick off our project. I will see you there. In this lecture, we will set up the foundation for our final project. Before we dive into the internal logic of the traffic light class, we need to define how our main program will interact with it. We'll start by defining the interface and the high-level structure of our Arduino sketch. Our traffic light class needs to be easy to use. The constructor will take 3 pins for red, yellow, and green. We also need a public update method that accepts a brightness value. This allows our main loop to drive the logic without knowing about the internal state machine. In our main.ino file, we include the necessary headers and instantiate our objects. We create a traffic light object on pins 11, 10, and 9, and a potentiometer on analog pin 0. This high-level view shows exactly what components our system uses. The loop function remains incredibly simple. We fetch the current brightness from the potentiometer and pass it to the traffic light's update method. This demonstrates the manager pattern. The main loop coordinates the flow of data between independent objects. By defining the interface first, we create a contract. As long as the update method exists and takes a brightness value, we can change the internal logic of the traffic light later without ever touching our main loop code again. With the main structure ready, it is time to build the engine. In the next lecture, 07.03, we will dive into the header and implementation to set up the traffic light class and its internal LED components. See you there. Now that we have our main program structure, it's time to build the traffic light class itself. In this lecture, we will set up the class definition and see how to use composition by including 3 LED objects inside our traffic light class. This is where we define the physical components of our system. In our header file, we first include LED.h. Inside the private section, we declare three LED objects: red LED, yellow LED, and green LED. This is called composition. Our traffic light has 3 LEDs. We also prepare an enumeration for our states and variables for timing, which we will use later. In the CPP file, we use the member initializer list to set up our LED object. Because the LED class requires a pin in its constructor, we must pass the R pin, Y pin, and G pin here. We also set the initial state to red and capture the storing time using nillies. Why use composition? By embedding LED objects inside the traffic light, we encapsulate all the hardware details. The TrafficLight class acts as a high-level manager, telling the individual LED objects when to turn on or off without needing to know which pins they are connected to. Our traffic light now has its LEDs ready. But a traffic light isn't very useful if it can't switch colors. Coming up next in lecture 07.04, we will add the methods to initialize and toggle between our red, yellow, and green LEDs. See you there. With our LED objects successfully initialized through composition, we now need a way to manage them as a group. In this lecture, we will implement a utility method to turn all LEDs off at once. This is a critical step for ensuring that only one light is active at a time during state transitions. In a traffic light, we must ensure we never have two conflicting lights on at the same time. The set all off method serves as a reset for our hardware. It simply calls the off method for each of our private LED objects, red, yellow, and green. Notice how we are interacting with the LEDs. Even though traffic light doesn't inherit from the LED class, it owns them. When we want to change a light, we send a command to that specific object. This allows us to use the PWM based on method from our LED class to support variable brightness later on. By calling set all off before switching to a new state, we guarantee a clean slate. We now have the ability to control the physical lights, but who decides when they should change? In the next lecture, 07.05, we will implement a state machine to automate the logic and handle the sequence from green to yellow to red. See you there. In this lecture, we will implement the brain of our traffic light, the state machine. Instead of using messy if statements, a state machine allows our object to clearly define which state it is in red, green, or yellow and handle the transitions between them professionally. To make our code readable, we use an enumeration. In the header file, we define traffic state with 3 values: red, green, and yellow. We then create a private variable called current state to keep track of which light is active. Inside our update method, we use a switch statement on current state. This structure ensures that the Arduino only executes the logic relevant to the active color. If the state is red, it only runs the red logic, ignoring green and yellow until the state officially changes. A state machine is all about transitions. Right now, our lights are on, but they don't change yet. By using this pattern, we have prepared the ground to add timing logic next. When one timer finishes, we simply update the current state variable. and the switch case handles the rest automatically. Our state machine is set up and ready to drive the logic. But a traffic light needs to know how long to stay in each state. In the next lecture, 07.06, we will implement time functionalities to handle the waiting periods between states. See you there. Our state machine is set up, but currently, it doesn't know when to move from one color to the next. In this lecture, we will implement the timing logic. We'll use the non-larking-millis function to ensure our traffic light stays on each color for a specific duration before automatically transitioning to the next phase. In the header file, we define constants for our durations. We'll set red and green for 5 seconds each, and yellow for 2 seconds. We also used the last change time variable to track exactly when the state last switched. Inside the update method, we compare the current time with last change time. If the elapsed time exceeds our duration, we perform 3 steps. First, turn off the current LED. Second, switch the state variable to the next color. And third, update last change time to the current time. The same logic applies to all states. When green finished, it switches to yellow. When yellow finishes, it loops back to red. Because we use millis, the Arduino is never stuck waiting, allowing it to perform other tasks like reading sensors simultaneously. Our traffic light is now fully automated. It cycles through the colors perfectly. But to make it truly interactive, we need a way to control its brightness. In the next lecture, 07.07, we will create a dedicated class for the potentiometer to handle our analog input. See you there. In this lecture, we will wrap up our hardware components by creating a dedicated class for the potentiometer. Instead of calling analog read directly in our main code, we will encapsulate that logic into an object that can provide us with refined data, such as a map brightness value ready for our LEDs. The header is very straightforward. We store the analog pin as a private member. For the public interface, we have the constructor and 2 methods: getValue to get the row 0 to 1023 data, and getBrightness, which will return a byte from 0 to 255. In the implementation, the getBrightness method is the most useful. We use the Arduino map function to convert the 10-bit analog input into an 8-bit value suitable for the analog write functions we used in our LED class. This keeps the math inside the object and away from our main sketch. Now, whenever you need to know how bright the lights should be, you simply ask the potentiometer object for the brightness. If you decide later to add a smoother filter, or change the mapping range, you only need to change it inside this class, and the rest of your system will continue to work perfectly. We have all our components built and ready. In the final lecture of this project, 07.08, we will put everything together to modify the LED brightness using the potentiometer while the traffic light cycles through its states. See you in the finale. Congratulations! We have reached the final step of our project. In this lecture, we will integrate our potentiometer class with our traffic light system. We will see how the brightness value we capture from the knob is passed deep into our objects to control the physical intensity of our LEDs in real time. The magic happens in the main loop. We use the getBrightness method from our Potentiometer object to get a value between 0 and 255. We then pass this directly into the TrafficLight's update method. This is a perfect example of how objects communicate. One provides data, and the other consumes it. Inside the TrafficLight class, the update method receives that brightness byte. Regardless of which state we are in, red, green, or yellow, the current LED is told to turn on with that specific brightness level. Because our LED class uses analog light, a physical light responds instantly as you turn the potentiometer. Look at this clean data flow. The hardware reading is transformed by the potentiometer class, passed through the main loop as a simple variable, and finally used by the TrafficLight to command the LED objects. This modularity is the essence of professional Arduino OOP. When you run this code, you'll see the lights cycling through their 5-second intervals, but you can also dim them or make them brighter at any moment. You've built a multitasking, object-oriented system that is easy to read and even easier to expand. You did it. You've successfully completed the TrafficLight system. But this is just the beginning. In the final section, we will wrap up the course, review best practices for OOP, and discuss how you can improve this project even further. Join me in the next lecture, 08.01, for the project conclusion. See you there.